Okay, we're continuing with part 2 of our chapter 21 discussion on musical sound. Let me dismiss my image and let's go here to sound intensity. The intensity of sound depends on the amplitude of the pressure variations within the sound wave. The human ear responds to intensities covering the enormous range from 10 to the minus 12 watts per square meter, the threshold of hearing, to more than 1 watt per meter square, the threshold of pain. The If you go to, I remember, I, I like the now I don't remember what they're called, the number 3 dinners here in San Antonio, and I made the mistake of sitting right up front, and boy, by the time uh, I ended the evening, they were my ears were ringing. So you have to be careful when you attend a concert. So the here, because the range is so great, intensities are scaled by factors of 10, with the barely audible 10 to the minus 12 watts per square meter as a reference intensity called 0 Bell, unit named after Alexander Graham Bell. A sound 10 times more intense, 10 to the minus 11 watts per square meter, has an intensity of 1 Bell, which equals 10 decibels. We normally speak in dB, in decibels, not in bells. And here's a chart decreasing intensity. Jet airplane 30 meters away is 10 to the 10 to the 2 watts per square meter. Air raid siren is 1 watt per square meter. The conversation in a home 10 to the minus 6. And you're looking over here at this column. The jet airplane is 140 decibels. The air raid siren 120. Conversation is 60. A whisper is 20 decibels. The rustle of leaves 10, and the threshold of hearing is called 0 dB, 0 decibels. Now, if you look at the busy street traffic, it's 70 decibels. And you might think, oh, 140 decibels, well, that's double. No, it's not, because it's on a logarithmic scale. The if the busy the busy street traffic were to double, it wouldn't be 140. You would go from 70 to 73. 3 dB is a doubling of the intensity. So if you go 6 dB, if you were at 76, you quadrupled the intensity of the traffic noise. So that's something to keep in mind. It's doubling 70 to 140 decibels. That's a big leap. When you double it, it would be 3 dB. 73 is double the busy traffic noise. Let me sound intensity is purely objective and physical attribute, and a physical attribute of sound wave, and it can be measured by various acoustical instruments. Loudness is a physiological sensation. The ear senses some frequencies much better than others. A 3,500 hertz sound at 80 decibels sounds about twice as loud to most people as 125 hertz sound at 80 decibels. Let me see if this is a good point. I think this is a good time to stop the share. Oops, let's go back up here. Let's stop the share, and I've got a little meter here. You can do a lot with a phone. So this is, whoa, lost my battery pack. This is a sound level meter, and you probably can't see it on here, but the light blue, it actually says quite instead of quiet. The green one is speech. The yellow one is noise, and the red one is danger. So this is just a sound level meter. I'm trying to remember what it said. The normal conversation was. I think it said it was about 60 dB, and I'm somewhere around there. If I were to increase my volume, see, it gets even. It was almost reached into the danger zone. But if I start speaking in a whisper, see how it goes down to almost into quiet. So here's a sound level meter, and you can you can see the intensity of the sounds you're hearing when I go to church on Sunday morning. Sometimes I pull this out because sometimes our praise and worship band is a little loud, and so I put my AirPods in noise cancellation mode. I can still hear it, but just not as loud as they play it. Okay, so let's get back. Let's put this down and get back to the lecture. Okay, and let's go back to the share screen. And where is the PowerPoint? How did I lose it? I apologize for the delay, but I've lost my. Oh, here it is. Here it is. I couldn't see it. Okay. Sound. I think we already read this one. Let's go to the next one. We have no trouble distinguishing between the tone from a piano and a tone of the same pitch from a clarinet. Each of these tones has a characteristic sound that differs in quality, the color of a tone, or its timbre. Timbre describes all aspects of a musical sound other than pitch, loudness, or the length of a tone. Most musical sounds are composed of a superposition of many tones differing in frequency. You can see when you if you were to pluck a guitar string, you would get a first harmonic, a second harmonic, a third harmonic, and a fourth harmonic. So you can see how. I keep advancing it. If you were to take this third harmonic and superimpose this first harmonic, you see how you've got this third harmonic, but it's also going up and down like the first harmonic does. Now, the various tones are called partial tones or simply partials. The lowest frequency, called the fundamental frequency, determines the pitch of the note. A partial tone whose frequency is a whole number multiple of the fundamental frequency is called a harmonic. The composite vibration of the fundamental mode and the third harmonic is shown in the figure. So this is a composite of the fundamental and the third. Now, some instruments will produce only odd harmonics. So you'd get the first, the third, the fifth, the seventh, and so forth. And if you were to have a signal generator and generate with a square wave, you would get all the odd harmonics. So different musical instruments produce different harmonics, and that's why we can characterize them as we hear them. We can tell the difference between a trumpet, a clarinet, a saxophone, a flute, because they have if you want, a signature of the tones they generate. So here's the fundamental, here's a second harmonic, and here's a third harmonic. And you can see how if you add all these together, you get a composite wave. And this is what makes up a flute sound. The composite makes up a trumpet sound, makes a guitar sound. each instrument has its characteristic sound. And of course, as they all play in an ensemble, you get a combination of all these wavefronts coming at you, and it makes beautiful music. Okay, the quality of a tone is determined by the presence and relative intensity of the various partials. A pair of tones with the same pitch may differ in the relative intensity of the partials. Our ears recognize the difference between a tone played on a piano and the same tone played on a clarinet, and it has to do with these the quality, the number of harmonics that it has. Here's the piano C, and here's a clarinet C. It looks like it has a lot more because it has more zigzags, if you want. It looks like it has many more harmonics. And that's the end of part 2. Let me see if I can let's see if I hit play, will it? Nope, that's not the one I wanted. Let's go over here. And hit pick the rib. That's the one I want, but let's put on my sound beam. Let's see. Let's search sound beam. Sound beam, there it is. And let's turn this and back here and stop the share and see if I can position it to where there's little glare. Okay. Whoop. No, let me hit wrong one. This is it in non-spectrum mode. Oops, you hit the wrong one. That's just the sound wave. Part of you also seeing my voice come out on here. It's not really, you're not really able to see it, but if I put it in spectrum, you can see that there's a lot of different frequencies. This is like at the bottom is 100, 300, 1,000, 100, 300, 1,000, and then 3,000 and 10K. And you can see how there's all these. And you see the clarinet has quite a few harmonics in it. Anyway, Pick a Rib Part 2 by Benny Goodman, one of my favorites. Okay, and I think with that demonstration of the clarinet, and I know it's kind of a crude setup. If I were to have a true oscilloscope, we could see. I look for samples of like a flute capture or a trumpet capture. I couldn't find them, but the ones I found weren't very satisfying. But anyway, the key takeaway is that different instruments have different signatures, different harmonics that make up their sound, and that's how we can distinguish them. Okay, we'll end it here.